Okay. What Favonia said, as usual, you've got that? Everyone got that? Okay, I'm going to erase it. Alrighty. So where we got to last time is we were talking about, we set up the basic framework of what are called dependent types, where the central concept is the notion of families. Families of types indexed by types. That's the index by a type. That is the elements of a type. We're going to talk a little bit about that today. But in order to set that in more detail, because this is like the big concept. This is the thing that makes all of it, makes what makes dependent type theory. So we explained that there was and I first had to explain the sort of judgmental apparatus. And so I was explaining that there's this sort of simultaneous definition of a bunch of things, which would include definitional equivalences as well as these judgments like these. This says that gamma is a context. This says that A is a type. This would say that these are definitionally equivalent types, or I'll just write it like that. And we have M is of type A, and M is definitionally equivalent to M prime at type A. Okay, so those are the basic judgment forms, the basic setup. And then they have various structural properties. So they have structural properties, which I won't repeat here, but we have to state them carefully. That was part of our discussion last time, just to remind you, because we have to worry about, for example, we cannot always permute the context so that a variable of interest is last, because subsequent variables, their types, may depend on previous variables and things of this nature. So you have to be a little bit more careful in stating like what substitution is and stating what reflexivity is and so on. But essentially the same structural properties carry over in a slightly more delicate form. You have to be careful about. And we have various issues like another kind of structural property, which is new here compared to the propositional case, is that typing respects definitional equivalence. So that's a new thing, because in the simply typed case, there's no non-trivial definitional equality of types, and so this is never worth mentioning, because the types are just pieces of syntax that you write down once, and there's nothing to calculate about them being equal or not. It's quite completely trivial. This is just the identity relation. So we have that, and let me just write etc., by which I mean the other judgments like definitional equivalence here also respects the definitional equality of the classifier, and things respect the definitional equality in the context position. And what I left open is the exact technical formulation. So just to remind you, so we left open the exact formulation, and I was more concerned because what happens is typically people will formulate the type theory so that, for example, weakening rules or something like that are admissible rather than including them explicitly as rules. And I'm not so worried right now about like getting all those fine details down, because those tend to be important. Those details do tend to be important, but principally when you're doing meta theory. And really, so I'm being a little loose here, okay, about exactly what are the definitions. And if you look in the literature, every paper or every source, it's slightly different in various ways. Okay, so just FYI. So at some point we may find it necessary to really nail it down, and then I'll be sure to make those points. So that was the sort of general setup. And then the question that we have is that, well, it's all well and good to have this apparatus, but how do we actually populate it? And what I suggested, because it's good for purposes of illustration, what I suggested as starting points was some two familiar examples to keep in mind. So these are a primitive, I'll think of these as primitive types, and then we're going to need some other things as well, but we have to start somewhere. So I gave an example of a fairly obvious one where we could have, the sequences of natural numbers of length x. Okay, where the idea would be, this is, as I said, this could represent the family of types, so sequences, and then just for specificity of nats. It's not so important to me. What I really need to, what I really care about is that it's of length x. Okay. And this is a perfectly good example of a family of types. And, in other notational systems, people would write this something like this. They would say the family of types seq of x, x is in nat. That's like the notation you'd often see in textbooks, like and using a more set theoretic looking notation. So the point is, it's just the family of types that for every x in nat, I give you back a type, which is that. And the important thing is, because of the general considerations of the structural properties, we end up with a particular principle that says if m is n prime in nat, then seq of m and seq of m prime are the same type. So we expect that. So an example of that we went through last time is you would expect 3 plus 4 to be the same type as seq 7 maybe, or any other such calculation. So that's good. So we spoke about that. And then the idea is that if we have this definitional equivalence, and that because of this rule that we have here, this type in this type or you might as well consider identical, because they classify the same things. So that's the importance there. But then I noticed, I mentioned to you, okay, we do not get, and I mentioned this last time, that in general for x, y, and nat, you don't get that seq x plus y equals seq y plus x. Okay, and the reason is that, sorry, let me write it like that. It's not, that's going to be not derivable, or I could write it like that. This is not going to be derivable by the rules. Okay, and the reason is, for the sort of subsidiary reason, which is that it's not the case that you can derive that x plus y is definitionally equal to y plus x in nat, like that. This is not derivable in general. Now, you might ask yourself, why is this not derivable in general? And I just asserted that because I said that it is a true fact about the rules we gave. And the thing that you might reasonably, well, I haven't proved that, but the thing you might reasonably puzzle over is, if we had something like the eta rule for the natural numbers type, which says something that behaves like the recursor is the recursor, why can't I use that? Because maybe, let's say, x plus y is a recursor that's defined by induction on y, and this is some other function, because it's not written like a recursor on y, it's some other function. I wrote them p and q when we discussed last time. And you might say, well, this function on 0 behaves the way that 0 does, and it commutes with the successor in the way the eta rule requires, so therefore it should be that this is equal to that definitionally. And the answer to that is sort of no, because what you need is, so what I would like you to think about is, to apply eta, you need to establish an invariant, okay, about a candidate function. That is, about a candidate, we'll think about a candidate mapping, candidate M. And the invariant said that, it has to be that 0 for whatever it is, let's call it x, m, has to behave like the base case of the recursor that you're thinking about, and it has to be that if you look at the successor of x for x, m, that has to behave like m substituted for some y in p. You have these two things, and then from there, we get, and then we will get that therefore m is the recursor. Let me just write, x and y dot p. Okay, that was the rule we gave. And the point is there's an invariant. It says something governing M. Something about M has to be the same as something else about M, and then this particular thing about M has to be true. And here there's this kind of invariant going on, and here, because of the circularity. In other words, we can't sort of solve for P here in any obvious way. That is, I could replace N here, I could just definitionally replace this by 0 for xm and put that there. Okay, that's fine. But then I'd still have as a premise of my rule that this invariant has to hold, okay, which is some behavior about M on itself. And the definitional equivalence gives you no way of establishing that invariant, because what you need is a principle of induction. Okay? So what is missing here is that the eta rule is valid, but you pretty much have no opportunity to use it, that's a way of saying it, because there's no way to inductively establish such a thing. Okay, there's no principle of induction. And then what I was saying with the idea about synthetic and analytic judgments is that not only, it's not like I just, I made a mistake, I omitted a rule of induction. It's I didn't want a rule of induction in definitional equivalence, because that's what distinguishes definitional equivalence from maybe loosely speaking equality, okay, in a more looser sense or more familiar sense, is that it does not require proof. That is, there's no, to establish a definitional equivalence doesn't require, like, for example, an inductive argument. So in order to support that, what we did at the very end last time is I said, well then, how would you state? So we have definitional equality, and we decided that, okay, we're going to make our peace with that. Definitional equality is a relation that I will call sameness of algorithm or sameness of sense, and we'll just like live with that. And it's kind of an inductively defined thing. But anyway, I do want to talk about equality in a stricter in another sense, in a more familiar sense. So in particular, I'd like to be able to talk about, as we'll get to in a little while, equality of functions in a meaningful way. And I'm going to explain what I mean by that when I get going here. Okay, so the other thing is, but we wanted to say, how would we express these things? So this was a remark about definitional equality. So we introduced another family of types. We said, well, if you fix any type A, and you have x, y, and A, then we're going to associate a two-indexed family of types. So it has two indices, x and y, so it's a doubly indexed family of types, doubly indexed over A, where A is arbitrary. You have this for any type. Okay, so this is going to be thought of as a type. And it will enjoy the same kind of definitional principles that we've described. So something analogous to this, which I won't write here, will say it will respect definitional equality in both of those positions, and it behaves nicely in this respect. So the idea about it, and by the way, just notationally, we sometimes will write this as x equals a y. But I'll warn you slightly that sometimes that can be confusing, because if you're not that experienced with like the type theoretic meaning, then it gets it can be confusing. So I want to be careful about that. But a lot of times we'll write it like that. Okay, and we'll have other notations will come up too, but those are the principal ones for right now. So now we get back to something that I was establishing in the first couple of weeks of the class, which is the notion of proof relevance, okay? That we were talking about proof relevant mathematics, or that the idea about type theory is it's constructive, and the idea of constructivity is multifaceted, but one of the things that is really central to constructivity is the idea that proofs are mathematical objects. Okay? And so what's going to happen here is that if we're to think of this as a type, as I mentioned, by propositions as types, we could think of that as a proposition as well. That's just like, I'm encouraging you to just like treat those as synonymous. And so this could also be said to be a binary relation, a two-indexed family of doubly indexed family of types is a binary relation. I'll treat those terms as synonymous, okay, for the present purposes. We will come back later about some more refined idea about what a proposition might be and so on. But let's for now, we're just going to say types and propositions are the same thing. So the thing about them is that you have the notion of like a term P, to stand for proof, is here, which can be thought of, you can use various words for this. You can think of this as a proof that m is equal to m, that m is, I'll just write m is n. Okay, we'll just leave it like that for the time being. That is certainly one way to think about it. Another way to think about it is that it's an identification. I'm saying the same thing, but it's just kind of nice to think of different words because sometimes they have a different feel to them. So we can think of this as an identification of m with n. Okay, in other words, it's this term p, which populates this type, will represent a proof or an identification, some data, okay, that correlates or identifies m and n, that tells us that m and n are going to be interchangeable. So it's called an identification because it renders them interchangeable. This view comes up, for example, if I make an assumption. I'm able to make assumptions. I could have a variable z in my context, which makes an assumption that m and n are equal, and then makes a deduction based on that assumption. So that's perfectly reasonable. So the idea of a variable ranging over a type subsumes the idea of a hypothesis under which we're reasoning. That's the same thing. Okay, so we can think of it like that. And another kind of bit of terminology that will end up being relevant a little bit later is we can think of this as a path between m and n, and these are all, of course, within A. Everything here is, relative. These are known to be elements of A. So this is a path between m and n and A, and the concept of a path is meant to be bidirectional, in the sense that if I can go from m to n, if there's a path between m and n, which is an identification or a proof that they're equal, think of them the same way, then of course there's a path from n to m as well, because they're identified m and n, and we have p, a proof that they're equal. So obviously as m is equal to n, then n is equal to m. That would be the idea. And we can compose paths. That is, if I have a path from m to n and n to p, I can compose them and make a path from m to p. So I'm going to explain that in detail by the end of the lecture, but I just want to give you a flavor. So there's going to be these readings, okay? There's proof, there's identification, there's path. Sometimes people will say evidence here. I don't know, different words like that, okay? Sometimes people get nervous about using the word proof here. Personally, I think that I prefer it, but I also am aware that some people don't. So you could use the word evidence if it feels nicer to you. But the important point is that it's a term of the type theory that inhabits a type, and it represents, if you don't like it is, or it represents a proof that m and n are in some sense equal. So what I want to do is I'm going to axiomatize that, and if you're not familiar with type theory, it's going to take you a little while to get your head around the axiomatization of it. So in order to prepare you for that, what I'm going to do is first of all discuss some of the other apparatus of dependent type theory so that I have it available to me when I explain the identity type. So that's my plan. Okay? That makes sense? All right. So we'll come back to this in a minute, but this turns out to be a central notion. So we'll have a notion of equality, and the terminology, people will sometimes say, you'll see that this is sometimes called propositional equality. There remains in type theory some unsettled issues of terminology. That is, there are terminological traditions that have collided at this point. And so every time I say words like that, I always, like, if it were up to me, I would never use the word proposition. But this is pretty common, though, anyway, to that. And there are some possible confusions that will come up later because of other uses of that term. So let's just hold that in abeyance for the time being. Okay, so that's called propositional equality. One might, as I mentioned, I think last time, you might call it typical equality, but it sounds really weird to say that. So, but okay, so that's so you'll see that. So people will distinguish propositional equality from definitional equality. Already it's odd, right? Because probably, unless you have experience in type theory, you've never been trained to think of there being two different kinds of equality somehow. Okay, that's probably new. Like if you look in first order logic or something, that doesn't exist. Okay, so in this sense, there's something different. And the reason is in my opinion, the reason for it is that the computational aspect of constructivity. What is happening with definitional equality is it's representing equality by computation, just by what is in compiler literature is called symbolic execution. I don't know why. All execution is symbolic, if you ask me. But anyway, symbolic execution or something. In other words, it represents the way in which we just calculate 3 plus 4 is equal to 7. And so that calculational aspect is distinguished from an aspect of equality that involves reasoning. And in usual formulations of logic, one doesn't make any distinction between those. But I think the motivation for doing it, there probably are several, is to draw out the computational meaning of things. So we'll come back to that a little bit later. Okay, so now what I want to do is review the type structure that we started out with, and what I want to do is I want to generalize, okay, the propositional negative connectives, what I call the negatives, to their dependent form. And some of you will be familiar with this forms, and they're going to be like this. So what I'm going to do is I'm going to generalize what I wrote as A and B, which is the same as A cross B. So by now we're just going to switch back and forth between logical and type theoretic notation according to how the mood strikes us. So we're going to generalize the idea of a product into, and now terminology. This is another one of these terminology things. This is sometimes called the sum, and it's also sometimes called the dependent product, and probably it's called other things. So in New Perl, when we were doing this a long time ago, we resorted to stop giving them suggestive names and call them by their shape. So these were called sigma types. That way we didn't have any stumbling around on terminology. So it's kind of notorious that in New Perl, the various type constructors are named after their typographic form. Okay, so that's the way it is. Okay, so this is sometimes called the sigma type or dependent sum, which is confusing because the sum is generalizing the product. And it can also be called the dependent product. I'll explain what it is in a moment. But then that conflicts with the following thing, which is if we have A implies B, which is also written B to the A, or written A arrow B, depending on what you're doing, generalizes to, well, what could only be called the dependent product. And so that's where it's just a stupid thing that terminology has conflicted in certain ways. So sometimes I'll write a little X here just to stress that B depends on X. And that's the important thing, okay? So, for example, before I define what these are, I can certainly write down a type like this, is that for every X in that, see, I'm already doing it, okay. There exists a Y in that. I'll just pronounce it in the logical way, such that, I don't know, make something trivial up just for the sake of the discussion, so that in that, Y as the successor of X, maybe. I don't know, just something like that, just to write down a type that I have. So this is a type, and then you heard me already saying it. So logically, this corresponds to, on the logical side, this corresponds to for every X in a B of X, and this corresponds to exist X in a, oh, no it doesn't. This does, the other way around. Okay, yeah, that does. A B of X, okay? And actually, one could argue this, we might get into this, there's some discussion about the nature of existential quantification, which I will get to shortly. Okay, but if you give me that for the time being, then this is just read the same way as for every X in that. So sometimes it feels better to use the quantifier notation. And then maybe, just while I'm continuing in that vein, I might well write X, Y nat equal successor of X. And that looks more like familiar logic. And that's fine, and that's a good way to do it. And the point is that the propositions as types correspondence just says that there's no difference between those. You could actually, if you wanted to be perverse, you could write for all and sigma. You can do whatever you want, but typically we go one way or the other. Okay, so that's a way, like an example of a type that we can form with these. Okay, so in order to explain, I should explain what these two things are, and I think I'll start with this one because there's not a lot to discuss here. With this one, there's a little bit more to discuss. So let's start with the pi, so we know. Okay, so the formation rule says you can form a pi type. For now, like at this stage of the lecture, I'll probably write the little x there a lot, but it's just an indicator to mean that it could occur. So this is a type, okay, if A is a type, and assuming x is an A, B is a type, let me write the x here. In other words, it's a family of types. Oh, so the reason I chose this is that you notice I needed to have something to write here which would be a family of types. I mean, to be non-trivial. I could have written just one here or something, but to be non-trivial, I needed to have a type that it has x and y occurring in it, and so that's what I chose. Okay, that's why I chose the identity. Okay, just to get us off the ground. In a short while, we will have to ask ourselves a question about which families of types exist, and I'll come back to that a little bit later. Okay, so this is the pi formation. Okay, so it looks like that. So it's just telling us that if you think of this, mentally replace that by the quantifier, it's kind of what you would expect. The only difference, by the way, is notice that this quantifier notation only makes sense insofar as you're willing to identify propositions as types. Because in this position, you tend to think of this as propositional when you're writing it as a as a type. You're thinking of this as a sort of data, and in this position you tend to think of it as a proposition, but in any case they're both types. Whereas in conventional logic, there's a sharp difference. There's propositions and there's, types, the domains of quantification, and they don't really have much to do with each other, and especially like first order logic. And in that case, you really have a sharp distinction between data like NAT, which I chose here, and propositions, which are something else. But in the setup of type theory, that's all one big bucket, and everything comes together. So although that is like the attitude I take about it, it's perfectly plausible to be able to make a statement about all proofs of equality, that A could be an identity type itself, and I make a statement about all proofs of equality. That's a perfectly reasonable thing to do, and we will be doing that. So this could just as well be something that feels like a proposition as opposed to something that feels like data, okay, like the natural numbers. So you kind of have to keep that in mind. But having kept that in mind, then you can see that this would be the natural rule for it. And then the idea is we have for forming it, then the introductory rule says, we'll write the usual lambda like that. If uniformly in X I have M, which is an element. If I wanted to stress it, I would say that this has an X in it too. Shortly I'll stop doing that, but for right now I'll just mention that. Okay, which has this dependency. So the interesting thing is that the type of the output, so to speak, is indexed and determined by the actual input. So the input is X. Let's say it's a number for the sake of discussion. You have some term that computes something of a certain type. Its type is sensitive to which input you gave. So that's a twist, right? That's a new thing, right? In ordinary programming languages, you have nat arrow nat. So this guy gets to know about X because it's a nat, but the result type is fixed, like nat, and you don't have to say anything. There is no notion of dependency. But here I can have a function whose image is classified or broken up, or you could say broken up or fibered or other words like that, that says that according to what the actual input is, that will determine what the type of that guy is. So that's quite important. You wouldn't be able to read this as a quantifier if that weren't true. But the tendency is, if you think of this as like data, like functional programming, that's a little bit unusual. It doesn't come up so often in functional programming, except insofar as you have type quantification. But I will come back to the idea of type quantification and stuff a little bit later. And then the other thing we have is, and then really now I'm just going to amplify the point I just made. If you give me a particular argument, a function and a particular argument, then its application is, the type varies with the argument. Whatever the argument is, the type gets to know what that argument is, and you plug it in. So you can see that here. If f were such a function, then if I apply f to 7, then its type would be there exists a y such that y is the successor of 7, right? Something like that. Okay, you would plug it in. In other words, the type of the application is sensitive to the actual argument. And if I plugged in 8, well, then that would be 8. I mean, it's not one fixed type. That's the idea. Okay, and the beta-like axiom for this says what exactly you think, because it's the same as before, and my point is that this generalizes. And there's typical to take an eta-like axiom as well, okay, to write it like that. Lambda x m, where m doesn't have an x in it. So lambda x m x, and yet x is not in here. Really, I should write that out. Okay. Okay, but anyway, that's it. Those are the typical definitional equivalences that we use to govern the pi type. And then, as you probably know, if you look at these rules and you just say, pretend that b doesn't actually depend on x at all, because that's a special case. Let's say the x doesn't occur here, like think of this being nat. Then there's no difference between this and a arrow b in the case that x is completely independent, b is completely independent of x. And then if you check, then all of the rules that we gave before will be derivable in that particular scenario, and the same definitional equivalences will hold. So it's a proper generalization. That's the idea. But the generalization is there. So the point is that the elements of the product, the big product of a family of types, are functions, and that interpretation is necessary because it's expressing quantification. And the idea is that when you prove a universally quantified formula, in one way or the other, and now there's some trickiness here, but let me try to slide this by you. In one way or the other, you're defining a function that says, well, if you give me any x, I'm going to give you a proof, okay, of whatever it is I'm quantifying over. And that's of the essence of the constructive interpretation, is that a proof of a universally quantified formula is going to be a function, in the same way that what we said earlier, that a proof of an implication is going to be a function. So those are kind of the same. So this is expressing partly a fundamental commitment of constructivity to that type of interpretation, that where you think of proofs as having, I/O behavior, and you're classifying their behavior using types. So, okay. Okay, then I'll do another negative, and then I will start talking about the positives and their some complications that come up with the positives. Okay, so the other thing that we need to talk about then is what I wrote first before, which is this notion of a sigma type, whose name somehow never feels quite right. So the sum, you can write it like that. So this is a type, and it's a type under exactly the same conditions. This is a sigma formation, as it would be for the pi, and then we're going to have different introduction and elimination. Okay, so the idea is that continuing with this theme that it's going to be a generalization of the product, then I will say I will have an introduction rule. So what is the sigma introduction rule? Well, the idea is that the sigma introduction rule consists of pairs, mn, because I'm thinking of generalizing the product despite the fact that this is called the sum. And what I will do is say, I need the first component to be an A, but now the dependency. The dependency is the type of the second component depends on the first. And it's that sequential dependency from left to right here, that the type of this guy depends on the first element, the M itself, is what distinguishes it. And you can, what will happen is the Cartesian product will again fall out in the case that B doesn't actually depend on X, in which case we would write it as A cross B. Okay, and then once I finish writing, you'll see that it completely coincides. Okay, so that's that part. So this is a little unusual because, but it's important for the purposes of representing logic, for example, because if this is supposed to be an existential quantifier, then what we're saying is a proof of an existential consists of a witness, M. So if I say there exists a prime bigger than 11, then a proof of that, okay, is a prime, M, okay, maybe it's 13, that we'll plug in there, and a proof that N is bigger, 13 is bigger than 11, which is what I prove depends on what this choice turned out to be. So in other words, to get the interpretation of existential quantification to work, the dependency like that is necessary. So when I try to prove for F7, I want to prove there exists a Y. Well, a proof of F7 might be a pair consisting of, you know, in this case I already specified 7, so it looks like I probably am supposed to say 8, and then I'm supposed to say something about the equality. That will turn out to be reflexivity once I finish explaining everything, but this will be in there. Okay? So it'll be in, well, it'll be in what I really, what I want to say is a proof of this formula, okay, is going to be, a particular proof of this formula is going to be like 8 and reflexivity. So we'll get to that in a minute. So that's how that would go. So the point is that this is supposed to represent what is usually called constructive existence. And it's called that for the same reason that our treatment of disjunction was called constructive disjunction, or words like that, because you're required, in order to show that something exists, you're required to cough it up. Okay? That's the important point. You're not allowed to have a proof of an exists, of a sigma, okay, unless you can tell me what it is. So some of you may have, you know, seen there's a well-known little proof saying that there are irrational A and B such that A to the B is rational. Have you ever seen that proof? Okay. You end up giving that proof and you never end up saying, well, which one is it? Okay, you never actually cough up what are the irrational A and B. Okay, so from a constructive point of view, one would say you didn't prove what you said you proved, that you were kind of you know, putting a little icing on the cake. It sounds nicer to say there exists a irrational A and B such A to B is rational, but actually what you proved is it's not the case that every irrational A to the B is A to the B irrational. That's what you actually prove. The proof actually proves it is not the case that any irrationals, when raised to the power, is irrational. That's what your proof proves. But by convention, social convention, you're allowed to claim that that is a proof of existence. Okay? That's what happens. So the constructive viewpoint is we disallow that social convention. Okay, we just say, well, it sounds judgmental, but anyway, you say, be honest. You actually proved, okay, that the other thing, that something cannot be the case. So just please say that, okay, and don't make it look good by turning it into an existential. That really is all it amounts to. So this is, if you watch Andre Bauer's lecture on the 5 stages or 7 stages or something of accepting of constructive mathematics, that's a parody of stages of grief, when you lose someone. That's like part of the issue, is that you just, it's not like, you know, if you read the historical literature from the 30s, Hilbert acted as though Brouwer was trying to destroy everything he had ever done in his career, and then he reacted very strongly against that. But actually, if you step back a little bit, it was just a plea for a certain kind of hygiene. Okay? So my point is that they're not really incompatible. Okay, it's just a refinement. You can. I like to think of constructive logic as a refinement of classical logic, in which we're a little more careful in certain ways. And if we are more careful in certain ways, then we get some benefits from that. And so it's like worth doing. It's not just a matter of like a preference. So that will all emerge in a minute. So in particular, the entire thing that we're doing this semester makes no sense. It degenerates to nothing if you insist on a uniform global adherence to these kinds of identifications that I was just talking to you before that are familiar from classical logic. If you do that, then the whole theory is non-existent. It's completely trivialized. So we will get a lot of mileage out of the fact that we're making these distinctions. Okay, so that's the notion of constructive existence. And now, for those of you who are following carefully at home, Henry, I will mention that the rules I'm going to give are not exactly the ones given in the hot book, because I have another point to make. Okay, so I'll write this. So it says, if we have this, so I'm going to follow kind of the general principle of inversion. And so I'm saying, you know, two things went into this thing, so I'm going to be able to get them back out by elimination. And so I'm going to say this is A. So that will be sigma elim 1 and sigma elim 2. And I'm going to say that this, I'm going to give a similar rule. And then here's the critical thing. I can form the second projection, but its type is dependent on whatever the first projection is. All right, that's necessary. And then we have the beta eta rules that you would exactly expect. And then we stated if we wanted the eta rule, we could do it here. So these would be the beta, these would be the eta. And of course, I really have to fill in all the types and stuff, but I'm assuming you can do all that. Okay, so that's what we would state here. Okay, so that's the notion of sigma. So the point I wanted to make, which I have now made, is that one could worry about this identification, but I'm saying it's almost a matter of doctrine that this is to be identified with that. Okay, with existential quantification. That is constructivism. Okay, is to do that, and so that's why a moment ago I said, well, one could question whether that's the right thing, but I'm going to say it's unquestionable. But it's unquestionable because that's a matter of doctrine. Okay, so that's so those are the rules. Okay. Good. Now that completes the generalization of the negatives. So that's all I need to say about the negatives. What I want to say next is about the positives, which is very important for setting me up to talk about equality. That's why I'm doing these things in this order. Okay? All right, so this is all pretty clear? Did I make any egregious errors? Favonia? No? Carlo? No? Okay, good. All right. So I'm having a good day so far. Okay. All right. So now the positives. So I want to review the situation with the positives. So this is the interesting thing here. So unlike the negatives that I'm not. So remember these, and so far what we've had amongst positive. There will be other things that will qualify as positive, but for now what we've had 0. A plus B, I'll start with those, and nat will be a positive as well, and eventually there will be others, okay? And there is not going to be here a dependent form of the sum, and there's not going to be a dependent form of nat, so to speak. It's not about changing the type. So with the negatives, I generalized the type, and I gave you rules that generalize it. Here the issue is that the positive elims, for lack of any better way to express it, reach into arbitrary types. And that's where the issue comes in. So for example, I'll remind you, okay, from the propositional case, okay, like that, the elim form looked like this. If you have m in a plus b and you have x in a, I'm just reminding you, and y in b, p in c, then case basically m x n y p was in c, where c is fixed. Okay, well, it couldn't but be fixed, because in the propositional case, they're all just fixed. There is no dependency, there's no family, so of course there was nothing for me to even say at that moment. Okay, but the idea is that they share a common. It's here, here, and here, and they share a common thing. So C captures the join point, right? C is the type of, we could say, the context or the join point. If you like to think of this kind of in programming terms, you're going to do a branch, and then when you're done, you're going to plug that into a surrounding context which makes use of the outcome of that branch. And so there needs to be a common type C here, which this is expecting regardless of how you went. So that's why that's the rule, okay, that you do in the propositional case. So it's a matter of the join point. Okay, so now in the case of the now we're in a setting which is dependent. And the issue, as I mentioned, is I'm not going to have some sort of crazy form of dependent sum here, although it'll be an interesting exercise when I'm all done here in the next few things I have to say. You'll actually be able to get the sum, the a plus b, out of this sum slash product thing, out of the sigma type, okay, provided that other things are around. That's what I want to warn you, provided that other things are around. So let's look at it in isolation and not assume it. So other things are around, so this will be like that. Okay, so the issue that I want to focus on is the C. Okay? And there are different ways to motivate this, but one way to motivate this is that think of this as, think of C as being a proposition for the time being. It'll help you to think that way. It's a type, but anyway, think of it as a proposition. So what we want to do is we want to be doing something like proof by cases of C. Okay, this is the kind of thing we want. We want to have proof by cases of C. So an example of the kind of thing we might want to do, which will come up in a moment, is if let me introduce part of it now. Let's define 2 to be 1 plus 1. Okay, this is the unit type. Okay, 2 to be 1 plus 1. Define true to be in left of the null tuple. Define false to be in right of the null tuple, and define if m and p to be the case analysis of m. I don't care because I already know it's the null tuple, and I don't care p. Okay, so write it like that. Just as an absolutely gratuitous aside, I like this definition a lot because it tells you that the old Lisp tradition of regarding if as a special form is mistaken, because there's nothing special about this, because there's a bound this is a binder here and this is a binder here, and you don't evaluate under binders. It just so happens we don't name the thing that we bind, but there is a bound variable there, so there's nothing special about if. Okay, but anyway, that falls out of that interpretation. Okay, so now if you look at the proof by cases of C, okay, what's going on here, if you want to do proof by cases of C, the thing I'm going to want to do is I might want to prove something like this. I might want to prove for every x in 2, this is a nice motivation for what I want to do, there exists, oh, no, I'll write it like this. I will write or, my point is I want to get or. One of two things will happen. Either x is true or x is false. So that's a trivial but reasonable thing to prove. I might want to prove this as a theorem. Okay. So, so this is not the good example. This is a good example of something else. I want to get a good example of reasoning from. No. It is a good example. No, that's sorry. Yep. I confused myself. Never mind. The sum I want to split on is there's a sum here and a sum here, and I confused myself for a moment. So I want to do this by case analysis on that sum. Okay. Sorry. So I want to do a case analysis in that sum. So the point is that what I'm going to do is I'm going to do two cases, and the case I'm in, the thing I have to prove is going to depend on which case I'm in. So the subsidiary case analysis will be either prove, I'll prove this in the evident way, or I'll prove this in the evident way. I'll have to do both of these because there are two cases. There are two cases, and I'll have to prove both of those. So the point is that when I do the case analysis, that is when I do the elim out of 2, the type of the case analysis that I'm doing will depend on the choice of x. That's all I'm saying. So proof by cases of C, you must flow the M, the branch, into C. So the rule then looks like this. You have M in A plus B, and for Z, generic in A plus B, I have a predicate. Let's write it C sub Z is a type. So I have a predicate over that sum. So this is in my little example here, this is my C. The matrix of the quantification is my C. And then what do I do? And now here's the interesting thing. I case analyze, and I say I have to have n, let's call it, which is now in left of x for Z in C, and y in B, and that's P. So I have in right of y for Z in C. And now altogether case, and then I like this notational convention. I put in brackets. This is called, by the way, we need this terminology. This is called the motive. And I'll explain why in a minute. Of M x dot n y dot p is in what? M for ZC. See, I'm proving a particular, so I have a predicate, and I'm proving a fact about the particular M in question. That's what I'm case analyzing. So here, I'm case analyzing on the X. So the statement I want to make is about that particular M, which is X, which is this statement here. And the subsidiary things are, I flow in left of X for Z and in right of Y for Z. But in the case of the Booleans, if this is 1 plus 1, there's no point in having a variable of type 1. Because we already know by the eta principle that it's equal to the null tuple, so I might as well plug in the null tuple. In other words, I plug in true and I plug in false. So what happens is, unlike conventional programming languages, and then the reason I bring this up is it's going to raise a question in your mind, but I will do this. So in conventional, let's look at the derived rule. For 2, it says if you have this, and for Z in 2, C is a type, and if n is true, this is just the derived rule you get, and this is false, then the if M n P is M for ZC. That's the interesting thing, okay? That's like when you specialize the sum to the Booleans, as I've described here, then you get this as the elimination form. So the question you might ask yourself, if you think of this as more like programming than like proving. So with proving, you can say, well, this means specialize the predicate to the particular term, and that seems unobjectionable. That's fine. So in particular, the predicate in this case was like a sum of equalities, and that's a perfectly plausible thing to write down. And that's my C of x, and then I plug in. Okay, everything's cool. We can do that. But in a programming situation, if you want to think of it as code, then what this is tempting us to do is, this could also be, question mark, something like if m, then, and now here's, I'll just do something funny, nat and 2. I'll put question marks here because I haven't actually given you the machinery to write this example. But the idea would be, I could write a program like this that says, if m, then 17, else true, which in any conventional programming language that you know of would be ill-typed because the two branches don't agree. But no, that's false. The two branches agree. They agree perfectly. They agree that their type is, they both have the type, if m, then nat, else 2. Why? Because 17, when you plug true in, is that what I want to say? Yes, when you do the case analysis, that's what's being done here, case analysis here. 17 has to have type, well, if true, then nat, else 2, which is nat. And here, it's if true, if false, then nat, else 2, which is 2, and true has the type 2 according to the definition I gave before. 17 has the type nat. So in fact, there is a join point. There is a perfectly good join point. Okay? The only question is that a well-typed expression? Well, based on what I've given you on the board so far, the answer is no. But that's only because I've only been able to write down so much so far. So it will turn out shortly, I'm using this as a motivating discussion, is that it will be possible to write that as a type. In which case, you then have types for example, conditionals that are themselves conditionals. That's not true right this second if you just take what I wrote on the board as all there is. But I'm motivating for you what will come up very soon. Okay, so that's what I want to mention. Okay, but if you stick to like logic kind of motivations, then it's perfectly apparent that I would like to express what is this thing going on? It's an example of proof by induction. So remember, I started the lecture by saying, if you look at nat, the eta principle for nat is a little deceptive because it says if you can establish an invariant, which you would have to do by induction, then a certain equation holds definitionally. So that motivated me for saying, well, how do we express these proofs by induction? So that's what I'm trying to do now. So this is an example of a proof by induction. It's a degenerate proof by induction because it's merely a case analysis, but that's an example of a proof by induction. What I'm doing is I'm proceeding by analyzing all the possible introductory forms that can occur and accounting for them in my argument and getting the result for the m in question. Okay, so it's an induction principle. So the same thing is going to happen to us with the natural numbers type. This board is readable, yes? Is this? Yeah, okay.
Do you need the motive from the case?
Okay, why, what, sir?
You gave the motive for case, but
Yeah.
you didn't use one.
Well, because I was being sloppy. Okay, so I guess I should mention this as well, right? You're probably familiar, let me just throw this in right now. Yeah, probably I should have written here if, and wrote down the z dot c. Yes, I should have. Okay. But since I'm not really concerning myself with meta theory that much, and I'm not concerning myself with writing an algorithm, a program to do the type checking, to check the typing judgment, I'm going to be fairly loose about what exact notation I use. So that's all. Okay, so for example, you might have noticed I wrote lambda x dot m because that was the essence of what I wanted to say. When you're trying to write a type checker, one strategy often is to require you to specify the type of the variable. Okay, and we'll do that according to our whim, and I'm not going to insist, because I'm not really, there is a certain imprecision to what I'm doing. There are certain things I'm just not explaining or committing to very carefully in order to focus on what I think are more important ideas. Okay, so things like that, I'm going to end up being sloppy. Okay. Oh, why is it called the motive? Well, it's the motive for the induction. Your motive is to prove M for ZC. This is your motivation. Or you could think of it as the inductive hypothesis, except that in the case analysis, there's no hypothesizing going on because it's just a case analysis. But one can think of it like that. And I think Connor McBride or someone like that introduced that term. I never had a good word for it, and thankfully someone came up with a good word for it. So it's called the motive. So we'll often explain that. I'm like so happy to have that term. I never knew what to call that thing. Okay, so that's what's going on there. Okay, so now continuing with the negatives. Let's look at what happens with the recursor with the natural numbers, because this is kind of how I started out today, motivating. It says if you have a natural number and the motive is indexed by natural numbers, then I say if I have n is a proof of 0 for ZC, written like that. And now here's the interesting thing, and you're exploring this variation in your homework in a way, so you'll see this. Let me write it down and then I'll explain what's going on. So this is successor of x for z. Oh, no, it's not. That's a lie. X for ZC, prove P is successor of X for Z and C. It's exactly what you think. Then the recursor of M and, well, okay, let's be official about it. Z dot C, that's the motive, that's the argument, that's the base case. And now we have two things here, that's the point. That is a proof that M for X, or M for ZC. Written like that. Okay? So it almost is just a straightforward generalization from the non-dependent case. In the non-dependent case, you don't have that. Okay? And you just miss out the 0 for ZC. You just get a C here, and you get a C here, and you get a C here, and you don't need the X around. And we asked you for homework to show that the version with the X around is interderivable with the version without the X around, provided you have products. And so you're going to do that for your homework assignment. But here, I don't get a choice. And the reason is because of the dependency. I have to know what C holds of in order to reason that it holds of one thing more. So I need the X there. And so that's why it looks slightly different. But apart from the fact, so if I had thought ahead a little bit better, I might have done the version that I showed you for Gödel T with that X in there so that it wouldn't look different. So, well, next time. Okay, so, and then you get the exact same sort of definitional equalities you would expect. So if we have for 0, x, y, p, well, this one is just exactly the same. That's n. And then there's one more, z dot c, successor of, let's call it m. And then it's exactly what you think, which is you plug in m and n for, m and, oh no, the recursive call. So this is always ugly to write down, sorry. You can look it up. You call yourself recursively on the predecessor, and then you plug that in for x and y, and that's p. So it's exactly what we had before, except for the fact that I do this, okay, and plug that in. So that's the same. If you wanted, these are the beta rules. If you wanted, you could take an eta rule, which I will omit here. You could write it down for yourself, what it would be. But it's not going to help you a hell of a lot, because that same issue about which definitional equivalences are provable, it's going to be exactly the same. So you can put in an eta if you like, but it's not going to address that issue of induction. But this itself, the formation rule of this guy, does address the issue of induction. Okay? And an example of that is the following. I'll just make a simple one. A simple one is you can prove for every x in that if x is 0, then false. Okay? And the way you're going to prove this, I'll leave this as an exercise. But the way you're going to prove this is this is going to be a lambda, and then you're going to do a recursion. Well, I missed out the motive. You're going to have to figure out the motive and all that. And x, and then stuff will go here. It'll look like that.
The arrow is the outer connective there?
Did I make a mistake?
No, I think the arrow is the outer connective.
Yeah, the outer. I think I want to say that. Okay, it's not the case. Oh no, that's false. So you're not going to prove that. That's false. I want to say successor of x. How about if I say this? Okay. I was thinking of one of the Peano axioms. Okay, the successor is not 0, and I wrote it down the wrong thing. So you wouldn't have been able to prove that. Okay, but this you'll be able to prove, I hope. Okay, you'll do that. So that's an exercise. Okay, I think you can just do that. And the point is, obviously, it's a proof by induction, and this recursor is the proof by induction. So from a programming point of view, the proof by induction is the primitive recursive function. That was the whole point of Gödel's T, was to give an interpretation of Peano arithmetic in terms of computation via these recursors. That was what he was doing. And in fact, what you can do then is give a proof of consistency of arithmetic that amounts to proving the termination of all the functions definable in Gödel's T, and then that will give you the consistency of arithmetic. So obviously that theorem is independent of arithmetic, but it's a way of explaining why arithmetic is consistent in the usual way that one does. You just try to isolate which is the unbelievable thing, and you use that to show that something else is more believable. Okay, so that's what we do. And now the next thing is a hard exercise, okay, because it requires something I haven't given you. So this you'll have to get later, okay, which is if you have one of the other Peano axioms, which, and I think you can guess what I'm going to write. If two successors are equal, so the injectivity, then their predecessors are equal. And this I'll leave as an exercise, but as of today you can't do this, okay, but later, so to say. Okay, but it would be worth your while to figure out why you get stuck trying to prove this. Okay, you're going to get stuck. If you just follow your nose and try to do something, you're going to get stuck. And what I will do at some point soon is give you the machine you need, the mechanism you need in order to get unstuck. And in fact, it's related to the next topic that I want to mention, which is the other form of product type. So let's do another example, which is the sigma variant. And this is actually the one that's in the book. So let me just write down what it is, and then I'll explain. So the idea is you do elimination as pattern matching. In other words, you phrase it as an induction principle. It seems very strange to phrase it as an induction principle because the only thing there is in a pair in a sigma type is a pair. So what are you inducting over? Well, what you're inducting over is the case analysis, of which there's one case, but you get access to the two components. So that leaves the following thing. So like here, I do two cases and I get access to the underlying data. Well, here I'm going to have one case and I get access to the underlying data. That's what's going on. So the rule will look like this. And I bring it up for a reason. So let me write it down first. Okay, and now we have motive. I almost wrote cross. Sigma x and a b of x. Right? C is a type. And then what you do is you say given x in A and y in B. So, compare, like you can see what it's going to, how it relates to what I've written over here on my left. Then do, I don't know, let's call this guy P. And what is it going to be a proof of? The pair xy for z and c. Okay. Then I will get something, I don't know, it's sometimes called split or other similar sounding things. I've forgotten exactly what written like that, but let's call it split for now. I think in NuPro we called it spread. Yeah, we did, I'm pretty sure. Okay, but anyway, that's like that. And you have xy dot p, and its type is m for z, c. Yeah, so that works, okay? So we write it like that. And what is the beta rule? Well, I think you could guess that. And you can probably guess what my question is going to be. So if I give a pair, let's call it M1, M2, and XYP, then you split, unsurprisingly, you split the pair and you plug that in. You plug that in for P. And that's the beta rule. And you can also phrase an eta rule if you like, and I'll just omitted that, which says anything that behaves like a split is a split. It's always the same. Okay, so you can write it like that. So now here's the trick, okay? So one is, for homework, you can define split from first and second. So that one you just do. The second thing is going to be a problem, which is define first and second from split. And this is, you won't be able to do it as of today. Well, you probably will because a lot of you know things, but if you just pretend that you only learned what I told you, then you won't be able to do it today, okay? Because there's a problem with doing this. And what I want you to understand, this would be a good moment for me to stop. In this case and in this case, I want you to understand on your own how you get stuck, because then that will motivate what I want to do next, because it's just useful. So if you it'll take you 2 minutes. I mean, just like write the thing down, follow your nose, and you'll realize you're stuck. Okay, and then I want you to see that. So just do that, and then next time I'll pick up with the thing I keep darkly hinting at, and then I will also start talking about the identity type again. All of this was by way of limbering you up for the identity type elim rule, because if you haven't seen that before, it's not like you're going to say, oh yeah, obviously. It's not so obvious, okay? It takes a while to get used to it. In fact, in certain ways, it still remains a mystery to me, I have to tell you, but I will do my best to explain it to you. And maybe by your questions and discussion, I can understand it myself even better. So there's a certain way in which I find it still a little mysterious. But okay, so I'll explain that next time. Okay, thanks.